Namaste. Welcome to this channel, Dr.ARM's Chemistry. Friends, we were discussing the transition metal carbonyls and related compounds. So last time we have seen or discussed the preparation of metal carbonyls and other points in the earlier lectures. And today we are going to study the structure of metal carbonyls. So this structure of metal carbonyls includes general representation. You can show the general representation that this metal is bonded to carbon and this carbon is further bonded to oxygen. Now there is triple bond between this carbon and oxygen, but during a bond formation with metal, carbon and metal, this triple bonding characters are decreased and the strength of metal carbon bond is increased. So it depends upon various other factors of this metal as well as the carbon. So we will discuss. There are mainly types, that is metal carbon bond. So we are having this metal carbon bond, another is carbon oxygen bond, and third is metal metal bond. So these three types of bonding will be discussed today. Now if we see the first, that is metal carbon bond, then we will see there are many evidences which are supporting the presence of this metal carbon bond, this carbon oxygen bond. So first important source of this, so we will see the first, that is carbon oxygen bonding, that is evidences. So the first evidence is that the carbon monoxide is evolved in the reactions of metal carbonyls. So carbon monoxide is evolved from reactions of metal carbonyl is very important source which indicates that the metal carbonyls contain carbon monoxide. Then another important evidence is that the carbon monoxide group in metal complexes can be replaced step by step by other ligands. So this shows that the carbon monoxide is also itself a neutral ligand and it can be replaced by any other neutral ligand by stepwise reactions. Third is the force constant of these pre-carbon monoxide. Force constant for pre-carbon monoxide and complex carbon monoxide are same, means they are almost the same values. Therefore the bond characters in carbon monoxide are much the same in that are present in the carbon monoxide molecule. So this is about the carbon oxygen bond formation or evidences about the next type of bonding. Say BUEC is metal carbon bond, metal carbon bonding or metal carbon bonds. So transition, if we see the transition metals, they are having, these metals are having N-D orbitals, N-D orbitals. So these are 5. So there are 5 N-D orbitals. Plus there is N plus 1 S orbital and plus N plus 1 P orbitals. So there is 1 N plus 1 S orbital and 3 N plus 1 P orbitals. So overall you will have 9 orbitals available in case of metal for the formation of various bonds, that is sigma bond, pi bond, etc. with the carbon of carbon monoxide. Now out of these bonding 5 orbitals, out of these you will see, out of these 5 orbitals are used for sigma bonding. 5 orbitals means it depends upon the complex. So in case of if you see, if we take the example of FeCO5, FeCO5, then in this case you will find that 5 orbitals are usually here in the formation of 5 sigma bonds. So similarly, depending upon the ligands available, the number of sigma bonds are produced, and it also results in the formation of pi bond, which is additional bonding, and it supports the sigma bond. So in overall, the strength of bond between metal and carbon is increased. So all these orbitals are utilized in the formation of bonding of different molecules, that is metal and carbon. So in case of FeCO5, we have seen 5 orbitals are used for the formation of 5 sigma bonds, and the remaining orbitals is, after using 5 orbitals, there are 4 orbitals. So these 4 orbitals means remaining orbitals we will see in general. So after using these 5 orbitals, remaining orbitals are used for pi bonds, for the formation of pi bonds, or showing pi bonding characters. So here sigma bonds are formed. Now we will see the sigma bonds. So these sigma bonds are formed by using electrons of carbon monoxide sharing with vacant orbitals of metal. So this produces the sigma bonds. Now, for sigma bonds, the anti-orbitals N plus 1 etc. all are used. Now here we have to see that the carbon monoxide is a neutral gas and it is having low basicity. And because of this, the ligand is expected not to form a stronger bond with metal ion or metal atom. So, if the ligand is very strong base, then it is expected to form a very strong bond with the metal. But this neutral ligand, carbon monoxide, is weakly basic and therefore it produces a weaker sigma bond. But after formation of sigma bond, this initiates the process for the formation of pi bonding. So the metal carbon pi bonding process is beginning. So this low basicity initiates the process of pi bonding between metal and carbon. Pi bonding between metal and carbon. We'll see how are these sigma bonds are involved or associated with the formation of pi bonds. So for the formation of metal carbon pi bond, all the metal carbonyls with filled d orbitals. So here after formation we have to understand that after formation of metal carbon sigma bond, when we consider this sigma, what is happening here? The electron pair of this carbon is transferred, is shared with metal ion. As a result of this, electron density on metal increases and therefore it shows the unfavorable charge separation. Means metal ion gains electron rich nature, whereas carbon monoxide becomes electron deficient center. So this is unfavorable charge separation. So this is the result of formation of sigma bond, that is the transfer of electron density from carbon monoxide to metal initiates the process of formation of sigma bond. So this sigma bond transfers electron density from carbon to metal ion, as a result of which metal ion gains high charge and carbon monoxide becomes electron deficient, and this produces unfavorable charge separation. So this process of formation of unfavorable charge separation, this results in the unfavorable charge separation. So in order to remove this unwanted or unfavorable charge separation, the process of pi bonding begins. And for this purpose, the metal ions are having filled d orbitals. The metal ion has filled d orbitals, and these d orbitals are possible when metal ion is in a low positive or negative oxidation state. Oxidation state means metal ion can be in zero oxidation state or low positive oxidation state, so that the d orbitals of metal are filled, and these d orbitals are available for the formation of pi body. So as a result of this unfavorable charge separation, the electron density which is accumulated on metal ion is required to be shifted back to carbon monoxide, and this process is showing that the pi electrons of these metal ion means the field orbitals, these field orbitals of metal ion are showing charge separation with removing the excessive charge on metal by transferring the d electrons available in metal to the vacant pi orbitals of carbon. So there is metal pi electrons are transferred to the carbon pi orbitals which are vacant. So these are filled and these are vacant. So as a result of this, there is formation of a pi bond. So you will find that there is drift of electrons. These electrons are moving from metal pi orbitals, filled pi orbitals. Electrons are moving from metal filled pi orbitals to the vacant pi orbitals of carbon. So this gives pi body, and electron pairs of carbon monoxide with carbon are shared or shifted towards metal atom, which produces sigma bond. So these two processes are having synergic effect. So these two processes are collectively showing synergic effect. That is, they are helping each other. So formation of sigma bond helps the formation of pi bond, and formation of pi bond strengthens the metal carbon bond. So strength of the metal carbon bond is increased in this way. So this is called a synergic effect. Now we will see how it is related to the bond orders. Means reduction in bond order of carbon monoxide. So you will find that the free carbon monoxide has bond order 3. So we are showing this triple bond. Triple bond. But when the carbon monoxide participates in bond formation, that is complex formation with different metal atoms or ions, then the bond order should decrease. The bond order should decrease. So we will discuss some examples in support of this. So when the carbon monoxide is free, the stretching frequency nu bar is for this carbon monoxide is 2155 per centimeter. So this shows that it requires very large amount of energy for the stretching of these carbon monoxide bonds. But when this carbon monoxide is terminal in the complex, it means this is bonded to metal ion, as a result of which the carbon monoxide bond order is decreased. So this stretching frequency for such type of terminal carbon monoxide decreases up to 2000 per centimeter. So this is about 2000 per centimeter. So you will find there is a decrease in the frequency where after formation of the carbon monoxide with metal. So here metal carbon bond formation is taking place, and this carbon monoxide, this terminal, is showing this touching frequency. So any effect which causes decrease in the carbon monoxide bond order, any effect that causes decrease in the carbon monoxide bond order, this bond order will increase the equally it will increase the increase in bond order of metal carbon. So metal carbon bond order is increased equally. So this is reflected in the stretching frequencies. Here bond order is 3, but in this case the bond order decreases. Bond order 3 will not remain as it is, it will decrease, means it will be less than 3. So we will see some examples to explain this. So if we take the example of isostructural and isoelectronic species, that is the isostructural species and isoelectronic species are like this. First we will take this NiCO4, then there is CO4 minus 1, and third is FeCO5 2 minus. So we have taken 3 species, in which case we will discuss how this bond order and these stretching frequencies are correlated with each other. So we will see first the bond order or we will see here the carbon monoxide and this metal carbon. So in this case we will have the values like this. We have the values like this. In case of this nickel tetracarbon only, the bond order is 2.64 and the metal carbon bond order is 1.33. In case of this CO4, this CO is carbon monoxide, cobalt, and this is carbon monoxide, so there should not be any confusion. In case of this, the bond order of this carbon monoxide, so these values are about this bond order of carbon monoxide, and it's both we have taken here. So we have mentioned this, there is no need to separately again represent it. So here the bond order is 2.14, and in this case the metal carbon bond order is 1.89, and here it is 1.85 and 2.16. So now we get the idea. Now we will see the stretching frequencies. Stretching frequency mu bar of this carbon monoxide are like this. In this case, the stretching frequency of carbon monoxide is about 2016. So this is given in per centimeter. In this case, the stretching frequency is reduced to about 1890, and in this case it becomes further less, that is 1790. So this will explain how the bond order changes and how the stretching frequency of the carbon monoxide also changes. So these two changes are in opposite to each other. So here you will see that when we consider this example MiC2 the bond order of carbon monoxide is 2.64. But in this case, the bond order is reduced, decrease of carbon monoxide. Here the bond order again decreases. Now in this case, when the bond order is 2.64, the stretching frequency is 2060. So you have to remember this relation. Now as this bond order decreases, the stretching frequency also decreases. So this is in case of carbon monoxide. Now this is also carbon monoxide. Here the bond order again decreases and stretching frequency again decreases. Now in case of, if we compare this with, correlate this stretching frequency with metal carbon bond, we find that as there is decrease in the bond order from pre-carbon monoxide, so in case of pre-carbon monoxide the bond order is 3, but in this case it becomes 2.64. The stretching frequency is reduced from 2155 to 2016. So as there is formation of metal carbon bond, so compared with these, the metal carbon bond is weaker here. This has bond order 1.33. So the metal carbon bond, nickel and carbon, is weaker. And this carbon monoxide bond is relatively stronger compared to metal carbon bond. But in this case, you will find that the carbon monoxide bond is weaker. Bond order is less, means bond is weaker, and in this case the bond order indicates that compared to this the bond is stronger in COCO4. Again, if we go to this example, the bond order of carbon monoxide is decreased, but equally the bond order of metal carbon bond is increased, and this is reflected in the stretching frequency of the carbon monoxide. So this shows that when we consider metal carbon monoxide, so there are 3 bonds. So when this bond is lower or weak, this bond, so here if we take, now we cannot interpret this 2.64 accurately here between carbon and oxygen. So we will just represent that these are 2 complete bonds and 1 dotted, means 0.64 units. So comparatively this bond order, the strength of the bond is 1, means there is 1 complete sigma bond and some partial pi bonds. So dotted line indicates pi bond and this sigma bond indicates, that is blue dash or solid line indicates sigma bond. Similarly here the sigma bond and these are 2 pi bonds. So there is 1 pi bond. So this is pi bond and this is also a pi bond. So it has 1 sigma bond plus fractional pi bonds. So we cannot actually write the value here. because it is not complete one, it is fractional. But here we can show that the bond order of carbon monoxide is decreased here. So carbon monoxide has bond order 2.64. So means there are two bonds, that is 1 sigma plus 1 pi bond plus 1 plus some fractional pi bond. So this is having fractional value of pi bond. So as this is having, this shows that metal carbon bond is approaching to two bonds, 1 sigma and 1 pi. But this pi bond is not complete. In this case, you will find that there are 2 plus some extra value of bonds. Means there is 1 sigma, 1 pi, and some fractional value of this pi bond. So in this way, you can find that the formation of pi bonding takes place. Now here we will show that these stretching frequencies will tell us how the carbon monoxide behaves. So any change made to increase the metal carbon back bonding, the carbon monoxide stretching frequency is still lower. So if the back bonding is negligible, then we can assume that the carbon monoxide is very weak. Carbon monoxide is very weak base. But as the carbon monoxide means pi bonding increases, it shows that the basicity of carbon monoxide also increases. So we can take number of such examples which will tell us how these. So we can have such number of such examples here, such as FeCO6 2 plus, which is having metal carbon bonds. The frequency of metal carbon bond is given. So if we take the example of FeCO6 2 plus, it has metal carbon stretching frequency mu bar is having value. Here this has no value. We will see another example of MnCO6 plus 1. So it has 460 per centimeter. Then another example is CrCO6. So it has 441 per centimeter. Third example is vanadium VCO6 minus. Then it has value so you can have these values like this. So it has not given any value. For stretching frequency of carbon monoxide is available. So we can have stretching frequency of carbon monoxide mu bar per centimeter. We will show this. This value is, in case of Mn, it has value 2090 per centimeter. This has 2000 per centimeter, and this has 1860 per centimeter. So there is also difference between the bond orders and stretching frequencies of terminal carbon and carbon monoxide and the bridging carbon monoxide also. So we can show that these terminal values, terminal carbon monoxide has stretching frequency mu bar is 1850 to 2100 20 per centimeter. Then symmetrical stretching frequency mu2 of carbon monoxide is also available. So it ranges between 1700 to 1860. 1860. Then in case of another symmetric stretching, symmetric mu3 stretching for carbon monoxide is 1600 to 1700 per centimeter. So these are some stretching frequencies which are reliable for our understanding. So there are so many examples in which we can find which shows the effect of ligands on stretching frequency, means other ligands on stretching frequency of carbon monoxide. So we will see few examples. The first is NiCO3 PF3. So this will have stretching frequency of carbon monoxide is 2111 per centimeter. Now we will have another example. There are so many examples we can show that if we take the example of NiCO3 PAB3. So this will have stretching frequency nu bar is 2060 per centimeter. Then in case of third example, NiCO3 PPH3, the stretching frequency nu bar is equal to 2069 per centimeter. So there are many such examples and values available in the literature. Now we will see the metal carbon bond length data. Metal carbon bond length data. So if you see, first the structure is then example, then bond and length, bond length, in PM. So first of all we will see the linear structure. Example is this AU CO2 plus the bond is here AUC, the bond length is 197 PM. Then second example is square planar. Then we can have a number of examples, but this will have a point group. It will have point group, difference, and number R1. So we have a number of examples of this type, that is RH rhodium CO4 plus the bond is RHC, the length is 195 pm. Second example is PD CO4 plus 2 plus the PD seal, bond length is 199 pm. Then PTCO4 2 plus, it has platinum carbon one length bond, the distance is 198 pm. So this is about the structure of this. Now we'll see another structure, that is tetrahedral. So we can show this structure as like this, as a regular bar. Here the point group is TD. Point group is TD. And number of bonds. Number of bonds. Bands, not bonds. The number of bands is 1. The examples. This NiCO4, which will have technically NiC bond, distance is 182 pm. Then in case of copper, CuCO4 plus CuC bond, distance is 196. Then third example is CO4 minus, the COC bond is 173 pm. And another example is FeCO4 2 minus, FeCO4 2 minus. That's FeC distance 175 per centimeter. Third is trigonal bipyramidal. That is GBP structure. So you can represent this structure like this. So here is metal at the center, and like this. Here the point group is D3H, point group D3H, and bond number of bands 2. Number of bands 2. Example, we can have is CO5 plus. So this has COC axial. It is the distance is 183 pm. Then another is FeCO5. The FeC distance. So one more bond is to be shown here. COC equatorial. This is 185, and in this case the FeC axial is 181. Then FeC equatorial is 180. Another example is MnCO5 minus in most salts in most salts. So this will have Mn, C axial 182 distance, and Mn carbon monoxide equatorial is 180. So in all these examples you will find that the axial bond is weaker. The axial bond is in this case 181 and 180. There is no much difference. In case of this Mn's equal, equatorial and axial, you will find that the axial bond is longer and the equatorial bonds, these are axial and these are equatorial bonds. So the equatorial bonds are shorter and the axial bonds are longer. But here in this case axial bond is also longer and equatorial bond is shorter. But here the equatorial bond is sometimes a longer bond. Let's see in case of cobalt. Then we will see another square-based pyramid. Square-based pyramid. Here the point group is C4B and bands, number of bands are 2. So you can have the example. So this square-based pyramid, you can have a structure like this. Like this. So we have like this. So you can have the values. Example is Mn CO5 Mn CO5 minus in pH4 P plus salt. So here Mn C distance apical this MNC distance central line from this, that is apical, is 179 pm, and Mn C basal is this distance. The metal is here and this distance. Any four, any of these four can be taken. It is 181. So comparatively, the MNC bonds at the base are longer and this apical bond is relatively shorter. Then we will consider another example, that is octahedral. So we know the octahedron. Here it has point group OH, then number of bands 1. The example is VCO6, where the VC bond is 200 ppm. Then in case of CO6, the CRC bond is 192. Then in case of third example, molybdenum MoCO6, the MoC bond distance is 206 pm. Okay. Octahedral. The example is tungsten CO6 and this WC bond is 207 pm. Then another is FeCO6 plus 2. It has FeC bond distance 191. Another example is ruthenium RuCO6 2 plus. Here RuC bond is 202. Then another example is osmium CO6 2 plus. It has osmium carbon bond is 203. Can have the bait. If we see the bait structure, bait, the point group is C2D and bands, number of bands are 2. So here the next structure is, so we can have number of examples, the planar triangular point group is D3H and number of bands 2. Then pyramidal structure, it has point group C3V and number of bands are 2. So in this way we can have number of such examples available in variety of literatures that are available in number of books. So there are many such books that is which are available online also. So we'll stop our discussion here and we will see in next lecture we will see the structures of various metal carbonyls in metal carbonyls of transition metals in various groups, that is group 7, group 8, group 9, group 10, etc. in the next lecture. So till then, goodbye, see you next time. If not, please subscribe to this channel and press the like button. Thank you very much for watching.